In the previous class, we looked at this problem of linear classification and how we could frame, and in the case where the points, you have two sets of points that are linearly separable, the problem of finding a hyperplane that separates these two could be posed as a satisfiability problem. That's what we saw first. But then we saw that this satisfiability problem doesn't necessarily give us a unique solution. There are in general going to be infinitely many solutions for this particular problem. So instead we added some more constraints, some more assumptions, saying that we don't just want any classifier, we want the one that maximizes the margin. And we formulated the following optimization problem to find the margin-based classifier. And the margin-based classifier is basically looking for so given two sets of points, x0 and x1, right? And the margin-based classifier basically wants to have sort of maximal separation between the two sets of points. If you look at the minimum margin from each of these two sets of points, this should be as large as possible. But when we tried to find the dual of this particular optimization problem, we saw that it had the following geometric interpretation, that if you take the convex hull of these two sets of points and want to find the minimum distance between these two sets of points, then so the dual problem was basically to find the minimum distance between these two, the convex hulls defined by these two sets of points. And we didn't do it carefully, but essentially the solution in the primal problem, we wanted to find what is the maximum margin. And in the dual problem, we wanted to find the minimum distance between the two sets of points. And it turns out that the margin is just going to be equal to, I think up to a rescaling. So the margin is going to be equal to half of the minimum distance between the two sets of points. And geometrically, what will happen is that the minimum distance between these two convex hulls, right? So there's a line that joins the closest point in this convex hull to the corresponding point in this convex hull. The solution to the primal problem will turn out to be the line that is perpendicular to this green line and passes through exactly the midpoint of this green line. All right. Although we didn't analyze that in detail with respect to the primal and the dual problems, but that is what will end up happening. And that's kind of geometrically intuitive. That's what you would expect to happen. All right. So this was an example where I didn't really solve for the primal optimization problem, or I didn't solve the dual optimization problem, but the dual optimization problem gave me some geometric intuition to the solution of my primal optimization problem. So this idea of duality is very helpful, not just in getting a numerical solution to your optimization problem, but also trying to get some intuition to the solution for your optimization problem. Right? It's extremely useful in various problems in computer science and physics and so on. All right. So I'll maybe end the discussion on these linear classifiers with just the problem. So what would you do if the two sets of points were not linearly separable? Right. So far, what we assume that we had two sets of points, x0 and x1, and there is a hyperplane that separates x0 and x1. But in general, this may not be the case. And in this scenario, one formulates the so-called support vector machine formulation, where you do the following. So now we're in the scenario where I have two sets of points. The dots and crosses, but I have some points here and some points, some x's here. All right. So it's not possible to find a hyperplane that separates the blue points and the green crosses. So what do you do in this particular scenario? Again, remember the objective is to come up with an efficient way of finding a hyperplane that does classification well enough. Right? This may not be the optimal thing to do in a sense, but it is an efficient thing to do. So in this case, what we could do is try to minimize the error in some sense. All right. So suppose that in this case, for this particular hyperplane classifier, there are two errors. This is one of the errors, this is the other error. So these are two misclassifications. And in a sense, you want to minimize the misclassifications. So let's suppose that the distance suppose I call this particular distance ui for this, in this particular case, and a misclassification on the other side. Suppose that the distance to the hyperplane is, let's say, Vj. All right, so earlier what we were trying to do was the following. I wanted the margin to be as large as possible. So what does that mean? Another way of interpreting the guarantee that the margin is at least t is that I can draw a slab of thickness 2t around the hyperplane on either side of the hyperplane, and I'm sure that no point lies within this particular slab. Right? Within this particular slab. But now I can't guarantee that anymore. Right? Now I have the property that there will be some points on either on the opposite side of where I want it to be. So I'll just leave you with the formulation of the problem. You can look up the book by Boyd and Vandenberg for a more detailed discussion. But so here is the optimization problem that one typically tries to solve. So minimize so you define variables 1, 2, or I in x0, we'll call these ui's plus summation j in x1 vj. So these ui's and vj's in some sense quantify by how much did you misclassify a particular point. Okay, so larger ui means that the ith point was misclassified. If ui is something that is large and positive, then it means that I was misclassified, and in some sense the distance on the opposite side of the hyperplane is large. Okay, so for example, if I take this particular point versus say this particular point, the v for this particular point would be larger than the v for this particular point. Okay, that's what it geometrically means. And if some of the UIs or the VJs are equal to 0, then it means that they were properly classified. Okay, so the geometric interpretation is UI or VJ equal to 0 means that they're correctly classified. And UI greater than 0 or VJ greater than 0 means that they're incorrectly classified. And by how much are they misclassified? That is given by UI, the value of UI or VJ. Right? And you have the following set of constraints. A transpose. So again, the minimization is with respect to the variables A, B, U, and V, such that A transpose Xi is greater than or equal to B. So earlier I wanted A transpose Xi to be greater than or equal to some B plus T, but now it will be B plus 1 minus Ui for I in X0. A transpose Xi should be less than or equal to B minus 1 minus Vj for j in X1. I'm sorry. It should be j. Okay. And I want every entry of U to be greater than or equal to 0 and every entry of V to be greater than or equal to 0. Note that in this case I do not have a T which corresponds to the margin, and I don't have a bound on the 2 norm of A. Okay. As it turns out, it's not necessary in this particular case, because in a way I have rescaled everything. It's not an obvious fact, but a little bit of reformulation will show that you don't really need to impose this norm on A. This will still guarantee that this in a way it is possible to reduce this to a minimum margin classifier. Okay, so here's a homework. Where is the extra 1 coming from? That's sort of the replacement of T. So in a way I've normalized out T.
And if it is linearly classifiable, are the solutions same?
Yes. So in other words, if they're linearly separable, then the solution for this will be this will give you a margin-based classifier. All right. So in that case, what happens is that all of the UIs will be equal to 0. All of the VJs will be equal to 0. Okay, that happens to be the solution, and
then it becomes a satisfiability problem.
it's a little more than a satisfiability problem, because I want A transpose Xi greater than or equal to B plus 1, A transpose Xj less than or equal to B minus 1. So there's a certain amount of margin that I am demanding.
You're not doing anything to the one.
You're not doing anything to the one, that's true. So effectively I can rescale A and B to get another solution. So sometimes you can impose the additional constraint that there are minor variations to this particular optimization problem. In some cases, you add an additional term So you want not just the misclassification to be small, but you also add the A as so-called regularizer.
What is equal?
So this last quantity is called the regularization term. Yeah. So your real objective function is this. This is what you want to minimize, but you add an additional term to make the problem a little smooth, or the function to be the overall objective function to be smooth, or get some nice properties. We'll explore that in a little detail in just a few minutes. Okay, so let's maybe ignore this. So the homework is solve for the KKT conditions. Okay, I want you to solve for the KKT conditions. So the first thing I want you to verify is that the optimizing A can be written as a linear combination of the xi vectors. Summation some alpha I xi. Okay, you'll see that the solution can be expressed as a linear combination of these vectors, but something more, find the i's such that the corresponding coefficient is not equal to 0. Okay. So you'll see, I mean, it won't be too difficult, but you'll see that the KKT conditions will ensure that the A star is given by so you have this sort of linear combination. If you want, let's maybe add the constraint that norm A square is less than or equal to 1. Okay, I'll explicitly add this constraint. Okay, for this particular problem, I want you to solve and first verify that A star can be written as a linear combination of the data points, but it will not be a summation of any arbitrary data points. There are special vectors here for which the alpha i's are not going to be equal to 0. Okay.
No, I think the function has norm A square. Has norm A square.
Yeah, norm A square less than or equal to 1. Yes. Not norm A. Okay. And here's some intuition as to which point should matter and which point shouldn't matter. So suppose I give you a solution, the optimal solution, all right? Let's consider the following set of points that I have drawn over here. Let us say that I added another point to this data set. Okay. Suppose I added a point over here. Do you think this new point, should change the solution to your original problem?
If it's far away, then no.
If it is far away, then no. I mean, just far away, it's correctly classified and far away, then it shouldn't change the solution, right? But on the other hand, if this point were somewhere over here, then should this change the solution? It should. But what if it is close by over here? Should this change the solution? Potentially yes, right? So this is the background geometric intuition that you should have. So with this intuition, I want you to try to solve this particular or solve for the KKT conditions and see what you actually get. All right? Okay, any questions so far? Okay, so now in today's class, maybe the next couple of classes, I'd like to talk about algorithms for optimization, right? So in the maybe some time ago, I discussed gradient descent, and we kind of analyzed the convergence properties of gradient descent. So recall that in gradient descent, what you do is you initialize a particular point, let's call it x0. Again, in this context, we assume that we are trying to do unconstrained minimization of some function f, typically a convex function f. Right? So f is convex, and want to find the unconstrained minimum of f of x. So you start with x0, and then you run the following iteration, xt plus 1 is equal to xt minus some delta t times gradient f of xt. You keep running this for a certain number of steps, and what we saw was that under certain regularity assumptions, so we saw that if the following properties hold, so for instance, if gradient f of xt minus or gradient f of x minus gradient f of x prime is less than or equal to some L times x minus x prime for all x prime. So there's some parameter L such that changing the value of x by any amount, at least by a small amount, doesn't affect the value of the gradient of f by a significant amount. All right. So if this happens, and if you start with a point that is not too far away from the actual solution, x minus x star is less than or equal to some d, x0 minus x star is less than or equal to some d, and you choose your t carefully enough, then after t steps, you're guaranteed that f of whatever x t, or in many cases you look at the average of x1 through xt, this is guaranteed to be less than or equal to f of x star plus epsilon. right? Yeah. So f of x star is the minimum value of f. You are within an epsilon of the minimum value of f. Okay, and this requires the number of steps that you have to run turns out to be some universal constant times L d square divided by epsilon. So these many steps of gradient descent are required. But you can also replace this with a different requirement depending on what you know. You need to know L, you need to know D, because you have to choose the step size carefully enough. It's just for a specific choice of step size. Right? Instead, if you had that gradient f of x is less than or equal to g for all x, so the gradient is bounded. It's not just that the gradient is smooth, it's also bounded. Then the number of the guarantee that we could give was that this is at most d times g divided by epsilon the whole square. So in this case, in the case where the gradient satisfies this so-called Lipschitz continuity condition, if this happens, then the number of steps that you need to run for grows as order 1 over epsilon. All right, so note here that the dependence on t is something divided by epsilon. On the other hand, if the gradient is only known to be bounded, then the dependence is now 1 over epsilon square, which is larger. Right? We're typically interested in small epsilon. So this is what these particular algorithms can guarantee us. Doesn't mean that these are the best algorithms to choose. Okay? But the fundamental assumption is that you know which regime you're operating in. That is, you know L or you know G and you know D. Okay? Or you have an upper bound on all of these. All right? But on the other hand, we can also prove lower bounds. That is, if I have any algorithm, so given L and L or G and D, you can come up, let's suppose that you're allowed to use any possible algorithm you want that gives you oracle accesses to the gradient. Any gradient, the only thing that you have access to are values of the function and the gradient of the function. You can ask for the grade. In every step, you can ask for the gradient at this particular point. At every step, you can ask for the value of the function at this particular point. But that is about it. You don't know anything else about the function itself. Okay? In this case, you can show that any algorithm, not necessarily gradient descent, you can use any update rule that you're free to choose any update rule. So any algorithm will require at least some constant times square root of L d square divided by epsilon. Using this vanilla gradient descent approach, we saw that we need something L d square by epsilon, but the minimum requirement for the best, or potentially the best possible algorithm, is square root of L d square by epsilon, or it could be greater. Right? No algorithm can give you this convergence guarantee with fewer than order L d square by epsilon number of steps. All right, that's the result that we have. So at present, there is a gap between these two quantities. What you can do using plain gradient descent is worse than what may be possible. It could be the case that this is the best, and this lower bound is not tight. Or it could be the case that the algorithm is not good enough and the lower bound is tight. I will not prove this, but we'll see that this is in fact tight. You can come up with an algorithm that converges much faster than standard gradient descent under these conditions.
You're not saying that epsilon square would be worse than epsilon because epsilon is usually very small, less than 1.
True.
But if I'm only have the gradient bound and I want to apply that condition, what if I just rescale the original function f of x, I just multiply by some huge constant, so that my epsilon, if I'm having epsilon 0.02, then I multiply the original function by 100, so that my target epsilon becomes greater than 1, becomes 2. Then will the second one?
So if you scale f by something,
Yeah.
and you scale this f by something, then this epsilon should also be scaled appropriately.
Yeah. So it will from 0.02, if I scale it by 100, it will become 2, and the second.
But then that would also change these quantities, right? L and D,
Okay.
right?
Okay.
All of those things would just change.
Okay.
So for the heavy algorithm, gradient boundary is required or Lipschitz continuity?
So in this case, this is in terms of the Lipschitz continuity, but you can also prove a similar result for the gradient. This is what we will typically operate in. So this is something that I proved in the class. I didn't actually prove this, but in many cases, this is what you go with. All right. Okay, so we'll do this in a sequence of steps. In fact, we'll see an algorithm that achieves this particular bound. But we also want to be able to design not just unconstrained minimization algorithms, but also constrained minimization algorithms. So I'll introduce a couple of frameworks or general approaches to designing optimization algorithms. So it will be not just one algorithm, but in some sense, a slightly broader class of algorithms. And so the first approach that we'll use is for the following class of problems. So I want to design a minimization algorithm, a gradient-based algorithm for a constrained minimization problem. And I'll start with the constrained minimization problem, the constraints being that the variables should correspond to a probability distribution or a probability mass function. All right. It's a specific example, so we'll explore that in some detail, but we'll see that all of this can be generalized even further. Okay. But even before that, let's try to view gradient descent itself in a slightly different way. I mean, all of these algorithms that you come up with, if you just look at the algorithm, if someone just presents these algorithms to you, it is not obvious how they came up with this algorithm. So it's useful to build some intuition, and that can be done by viewing plain gradient descent in a couple of different ways. Okay. So remember that in gradient descent, we had the update. So if you compare, let's say, gradient descent with Newton's method, if you recall the approach that we took to derive the Newton's method, what we were doing was the following. So we had the original function f. At every step, we tried to solve an approximate optimization problem. So instead of minimizing f in one step, we try to replace f with a different function g and try to minimize that function g. And in the case of Newton's method, the g was just the second order Taylor series approximation of the function f. Right? That was what we did. So have f, and the class of algorithms that we considered was this approximate or local optimization algorithms. So at every step, you say xt is the argmin over all possible x of some function ft of x, and it could depend on xt minus 1 also. All right, that's the sort of general framework for most of these iterative minimization algorithms, including gradient descent. So in Newton's method, you took ft to be second order approximation around the point xt minus 1. Let's look at the following case where ft xt minus 1, this is equal to f of xt, sorry, let me just take t instead of writing t minus 1 every single time. Suppose f of x comma xt is f of xt plus gradient of f at xt transpose x minus xt plus half of the 2 norm of, or some 1 by 2 delta times the 2 norm of x minus xt square. Okay. So basically in the second order Taylor series expansion, instead of using the Hessian, I just took the Hessian to be a scaled version of the identity matrix. Okay. So this is some function. What would be xt plus 1? Basically, you want to minimize this with respect to x, right? What would you get? So this should be easy because what we have on the right hand side is a convex function in x. Right? This is guaranteed to be convex because this is a quadratic and the Hessian is just a scaled version of the identity. So that's positive semi-definite.
Constant step.
Yeah, so what will xt plus 1 be equal to?
Xt minus delta times kz.
Yep, so it's just going to be xt minus delta times the gradient of f of xt. So we just recover plain gradient descent, nothing else. Okay? So you can view gradient descent as this local optimization framework wherein in every step you try to minimize this particular function, this particular approximation to the original f. Okay? Is this okay up to this point? Great. So then you may ask, how did we come up with this particular function over here, right? What would, in particular, what would happen if I replace this function with something else? And what is the purpose of this particular function? Now to understand that, let's suppose I did not have this term at all. I just had these two terms. What would I get? You want to minimize just this particular quantity with respect to x.
The linear approximation doesn't actually have a meaning, right?
Yep. So this does not have a minimum. It will be so effectively what is happening here, I mean, an intuitive way of thinking about what happens is, suppose you could also ask the following question where you had constraints. So instead of doing this minimization, so this is an unconstrained minimization problem. But suppose you were trying to solve a constrained minimization problem and you wanted to use the same approach. And at each step you wanted to find, you wanted to instead minimize this particular quantity. What would be happening is that you're taking a particular xt, you're finding the direction of negative gradient, and you're moving too far away in the direction of the negative gradient. Right? So assuming that instead of minimizing this over all possible x, so let's look at our min x within some bounded set, okay, of the first order approximation f of xt plus gradient f of xt x minus xt. All right. As it will turn out, if you want to minimize this, you should be moving in the direction of the negative gradient of f of xt, but what you get is minus infinity. So this first order Taylor series approximation gives you an algorithm that is too aggressive in some ways. You're moving along the right direction, but you're moving too far away along the right direction. And the inclusion of this term over here kind of slows down, or it makes the algorithm less aggressive in some sense. You're moving in the right direction, but you're not moving too far away in the right direction. And by changing the value of delta, this basically tells you how much you move in that particular direction. A larger value of delta. So if you stare at this particular expression, a larger value of delta would mean that this quantity becomes smaller and smaller. The effect of this term is less, but it means that you take a very large step in that particular direction. Conversely, if delta is small, you're not taking small steps, but it means that you're emphasizing this particular term more. Right? Remember that this term doesn't depend on the objective function at all. Right? The quantity that you're trying to minimize is f, and this quantity and this term over here, the third term, it does not depend on f.
That is the regularized.
Yeah. So this is what is referred to as a regularization term. Of course, in this case, you're not minimizing the function itself. So you can think of the gradient descent algorithm as running this minimization with a regularization term. All right, the regularization term being this particular quantity. Okay, so then the natural question to ask is,
What is
okay, some
Like how do you find k depending on the
no, k doesn't depend on the regularization term. So let's assume that k corresponding to the set of constraints, let us say, in a constrained optimization problem. In that case, this argmin would exist. If K is a bounded set, then this argmin is guaranteed to exist. But it ends up giving something that is not very useful, because at every point you are moving too far away, you are essentially jumping to the boundary every single time. That is what will end up happening.
This is what was called projecting.
Which,
X belongs to projecting.
if you impose, let's suppose that you run argmin of this such that X belongs to K, then what you would get is, then projected gradient descent is one thing that you would get. All right. So the natural question to ask is, what happens if I try to do the following? So xt plus 1 is argmin, maybe overall possible x of f of xt plus gradient of f at xt transpose x minus xt plus some distance between x and xt. Right? In this case, this is the L2 distance. Maybe in a different problem, where potentially you may also have constraints, maybe it makes more sense to choose a different d, depending on what kind of a problem you have. Right? So in such a problem, how do you choose d? And suppose someone gave you d, what kind of guarantees can you give? Right? So in the end, well, we want to try different things, but we also want some kind of convergence guarantees on our particular algorithm. So for what kind of d can we actually give convergence guarantees? All right. When I say convergence guarantees, I mean that I want to make some statement similar to this under conditions on, let's say, Lipschitz continuity of the gradient, and that the point is at least d close to the minimum. Then how many steps do I need to get epsilon close to the solution? Right. So we'll be very concrete now. We'll look at the very specific problem where the constraint set is that the variable should be a PMF. So the constraint set is the set of all PMFs on n variables. So the problem that we want to solve is minimize some convex function f of x. Let me call the variable p, subject to the constraint that p is a PMF. So means that pi is greater than or equal to 0 for all I, and summation I equal to 1 to n, pi is exactly equal to 1. So I want to run something similar to gradient descent. In fact, I want to do exactly this, and in such a way that I have a convergence guarantee on this particular problem, right, for that particular algorithm that I design. So in doing so, I'll introduce a general approach of choosing d. Okay, I'll choose d. So how do we choose d? There are a number of different ways. Each will end up giving you a different solution. Okay. So what kind of D's? So D is in some sense something like a distance measure for probability mass functions, right? In this case, probability mass functions, because that is what the constraint set is. I want P to be a probability mass function. The one natural way would be, irrespective of whether it's a PMF or not, I could just use L2 distance, and I would end up with the standard gradient descent, nothing new, right? But potentially I could replace this, the D over here, instead of using L2 distance, I could maybe use total variation distance. I could use, say, KL divergence or something else, right? In principle, I could just choose D to be some in my favorite distance, run the algorithm, and maybe it converges. But for a general D, I may not be able to derive or give any theoretical convergence guarantees. It may or may not converge. Right? But we'll see that, for example, if I take D to be the KL divergence, it does converge, and I can give guarantees. Okay, and there's a reason. We'll see that the KL divergence, in fact, has a special structure. So say we choose is the KL divergence. So the KL divergence between two distributions P and Q is summation I equal to 1 to n Pi log Pi by Qi, where here I am assuming that whenever Qi is equal to 0, Pi is also equal to 0. It is not a distance metric, correct? Some function. So D need not be an actual distance. So that's why I said something like a distance. It doesn't necessarily have to be a metric. In this case, it's not a metric. Right? And we'll see that we'll choose something that is not a metric, but it has some other special structure. The special structure that this has is that it belongs to a class of divergences called Bregman divergences. I defined this a long time ago in a different context. What is the Bregman divergence? So given any function f, so let me call this capital F to distinguish this from, or maybe I'll call this R. So given a function R from defined over some Euclidean space, you can define the Bregman divergence dr of x comma y x comma say y. So this is equal to f of x, r of x minus r of y minus the gradient of r evaluated at y times x minus 1. So R is for a given function R. This R could be totally unrelated to f, which we are actually trying to minimize. Okay. So basically what the Bregman divergence is the distance, is basically the, I'm sorry? The divergence is always going to be positive, and this quantity is going to be positive as long as R is convex, right? Because if R is convex, then you know that R of x is greater than or equal to the first order Taylor series approximation of R about y. And The Bregman divergence basically tells you how far away these two are from each other. Right? So this basically corresponds to the tangent plane passing through y at the point x. That tells you how far away is r of x from the tangent plane. Okay. So this is the Bregman divergence, and it turns out that you can express the KL divergence as a Bregman divergence. All right. How many of you have taken the information theory course? Okay, only some of you. Fine, but okay. How many of you have already seen KL divergence before? Okay, some more people. How many of you have seen entropy before? Okay, some subset, but it doesn't seem to. This doesn't seem to necessarily be an overlap. But yeah, whatever. So the Bregman divergence so the KL divergence is basically a Bregman divergence corresponding to negative entropy. So take R of P to be equal to summation I equal to 1 to n Pi log Pi. So this is called the entropy. Sorry, this is the negative entropy. Okay, entropy is convex, concave. Entropy is a concave function of the PMF. So the negative entropy is a convex function of the PMF. Right? So entropy is concave. The negative entropy is convex. Find the Bregman divergence between, let's say, P and Q. What do you get? This is summation over I Pi log Pi minus summation over I Qi log Qi minus what is the gradient of R? Yeah? Yeah, so it's 1 plus log P, 1 plus log P. So this would just be summation I equal to 1 to n 1 plus log Pi times Pi minus Qi. What do I get if I simplify this?
The gradient will be log of Q1.
I'm sorry?
The gradient part.
Ah.
Would it be 1 plus log Q1?
1 plus, okay. That's right. That's right. So this term and this term cancel. What can you say about this particular term? It's 0 because summation. It's because P and Q are PMFs. So summation Pi should be equal to summation Qi. So this quantity is 0. So what you end up with summation Pi log Pi minus summation Pi log Qi, which is nothing but sum over I Pi log Pi by Qi, just the KL divergence. Okay. So again, let's go back to our objective. Our goal is to see what happens to this particular algorithm, right? I want xt plus 1 to be argmin of f of xt plus the gradient, the first order Taylor series approximation of f around xt plus this additional regularization term, which I now take to be the KL divergence. So what I want is I want pt plus 1 to be equal to argmin such that over p in set of all PMFs, let me denote that Pn, of f of pt plus gradient f of pt transpose p minus pt plus the KL divergence between p and pt. Okay. Now I want some additional flexibility over here. So recall that in here I chose a parameter 1 by 2 delta. Right? Similarly, I'll use another variable parameter eta, but I'll multiply this here. Okay. I could have as well just done 1 by eta times the KL divergence between P and PT. They're equivalent. Because after all, I'm trying to find the argmin of this particular function. So I can, as long as the solution doesn't change, I can modify this function in any way I want. All right. Any questions? Okay, let me simplify this a little bit because I can do so. Note that does this term depend on P? The variable P. After all, I'm trying to find argmin, right? So if I remove the first term, it doesn't change the solution to, it doesn't change Pt plus 1. Similarly, if I remove this particular term, it is not going to change Pt plus 1. So this is the same as argmin over all PMFs P. Let me write that out explicitly such that Pi greater than or equal to 0 for all I, and sum over all Pi is equal to 1 of eta times gradient f of pt transpose with p plus the KL divergence between p and pt. Pi by pti. Correct? We can simplify KL divergence also. True. I effectively I can just remove that PTI. Because I have summation I equal to 1 to 1 pi log pi minus summation pi log pti. I'm sorry, I can't remove that. Right? But let's keep this. I mean, I don't want to simplify it any further. Okay. So I have this optimization problem. How do I solve? Yeah. Again, so firstly, is this a convex optimization problem?
Because F is convex.
Yeah.
Yeah, it could be convex.
It will be convex, and why?
Log part is convex. Like
Okay.
that side and F grad F is also.
Yeah, sure. So basically, P log summation over I pi log pi, that's the entropy, that is convex. This is basically entropy plus something that is linear in P. Right? So it's entropy plus a linear term in P. What can you say about the sum of two convex functions? That is guaranteed to be convex. Right? So it's convex. So I can, and okay, I'm sorry, I should say negative entropy. So this is negative entropy plus a linear term in P, and which is therefore convex. All right. Okay, so I can, that's number one. Number two, are Slater's conditions satisfied? Is there a point in the constraint set which satisfies all of the inequality constraints with strict inequality? Yes, it's trivial to take a distribution such that all of the components are strictly greater than 0 and strictly less than 1, right? For example, the uniform distribution satisfies Slater's condition. So Slater's conditions are satisfied and the function is convex. So I can just solve for the KKT conditions. If I can solve for them, then I'm done. I know that that is a solution. All right. Okay, so let's solve for the KKT conditions. So primal feasibility says that Pi should be greater than or equal to 0 for all I, and sum over the Pi should be exactly equal to 1. How many Lagrange multipliers do I need? I need n plus 1 Lagrange multipliers. Plus lambda I Pi plus minus lambda I Pi, because Pi should be greater than or equal to 0, or minus Pi should be less than or equal to 0. Sum over all j times pi minus 1. Right, so primal feasibility says this, dual feasibility say that lambda I should be greater than or equal to 0 for all I. Let me write the complementary slackness first. So lambda I pi should be equal to 0 for all I, which means that for every I, either lambda I is equal to 0 or pi equal to 0. Okay, and next is stationarity. So what is the gradient of L with respect to P? So it is the gradient, or let me take the partial derivative with respect to just pi of the objective function, which is the gradient of f of p. For convenience, let me say that say the vector g is equal to the gradient of f of pt. Okay, let me call this gt. So this is the dot product between the gradient and p, that is nothing but sum over I GTI times PI plus the KL divergence between P and PT. So this is summation over all I PI log PI divided by PTI plus I'm sorry? That's correct, because there should be an eta over here. Thanks for reminding me. So minus summation over I lambda I pi plus nu times summation I pi minus 1. Right? Did I get everything? What is this equal to? The first term just gives me eta times GIT plus I get log pi plus 1 minus log PIT, right, minus lambda I plus nu. Right, is this okay? Question? So this, we want to set the partial derivatives to all be equal to 0. Right, so this is equal to 0. So let me take the terms involving only pi to be one side and everything else on the other side, because this involves only p is the variable, right? PIT and GIT are constants here. So log pi is equal to minus eta times git plus log pit. Maybe I want to write that first. So it's log pit minus eta times git plus lambda I minus 1 plus nu. Right? Or pi is equal to pit times e to the power of minus eta git plus lambda I minus 1 plus nu. Right? So now I somehow have to find nu as well as the lambda i's. What do you think I can do? Yes, any suggestions? Primal feasibility will give you what? Sure, that's there. That in fact gives you nu. That's what will let you find nu. I think here this should have been negative sign. But how do I get rid of the lambda i's? I somehow have to be able to use the complementary slackness conditions, right? So complementary slackness tell me that either lambda I should be equal to 0 or pi should be equal to 0. Can pi be equal to 0? So when will pi be equal to 0? When lambda I is minus infinity. Lambda I has to be greater than or equal to 0. But there is a condition under which pi can be equal to 0. What is that? If pit is equal to 0. If pit is non-zero, then it's equal to, then lambda I should be equal to 0. Right? I'm sorry, lambda I can't be 0 only if pit equal to 0. Right? So if pit is non-zero, then lambda I should be equal to 0 because of the complementary slackness conditions. Okay, and what is nu? You just choose nu to satisfy the primal feasibility conditions. So you want summation over I, pi to be equal to 1. So in fact, the optimizing pi is simply going to be equal to pit e to the power minus eta git divided by sum over j equal to 1 to n pjt e to the power minus eta gjt. Okay, so then, well, we've solved the, in other words, we've derived this new algorithm now, where the regularization term, instead of using the L2 norm squared, I used the KL divergence. And so let's try to summarize this new algorithm. The goal was to minimize some function f of p subject to the constraint that p is a PMF on n variables. And the iterative algorithm that we've come up with is the following. So initialize some valid PMF P0 in Pn, right? That's step 1. And then for t steps, whatever that t may be, you run the following algorithm. So you find gt, which is the gradient of f of gt minus 1, which is, maybe I should write this in terms of t. So t equal to 0, 1 up to capital T minus 1. So gt is f of pt minus, sorry, just this. Right, so this is f of the gradient of f evaluated at pt. But now, instead of the standard gradient descent step, what you now do is your pt plus 1 is going to be equal to, or pit plus 1, the ith component of the next step is going to be equal to pit e to the power minus eta git divided by sum over all j pjt e to the power minus eta gjt for I equal to 1, 2, 3 up to n. Right? So this is a completely different update rule. Right? It's something like gradient descent, but it looks quite different. And the main reason it looks different is because we used a different divergence compared to the squared Euclidean distance. Right? And finally, of course, you can output pt, but in fact what we will do is output p bar, which is 1 by t equal to 0 to t minus 1 pt. All right. So instead of outputting the last point, I'm going to output the average of all of the points that I got across the iterations. And it turns out that for this particular algorithm, again, I will not be able to prove the result, but under the same set of constraints, you still have a similar a similar upper bound. So if you choose your eta carefully enough, then t equal to some constant times g square. So in this case, things will, g square times d divided by epsilon square. Steps are enough to get epsilon close to the minimum. All right. Achieve f of p bar less than or equal to f of p star plus epsilon. In the next class, I'll sort of generalize this. I mean, essentially the idea is the same. You replace D with another Bregman divergence, and you end up with a similar solution and a similar result. Okay. Any questions?